Hello students, this is a brief tutorial that will lead you through the guidelines to construct electron configurations as well as orbital diagrams. So we're just going to dig in. It is vital to be able to understand and be able to chart where the electrons are. That allows us to predict and understand chemical reactivity. The first guideline of electronegativity is the off-Baugh principle. The off-Baugh principle says that an electron will occupy the lowest energy position that can receive it. To guide us, we can create what I call the off-Baugh chart, and it's actually a reflection of the design of the sublevels within the energy levels. If we remember, every energy level holds an S sublevel. We'll just go up to 7S. In the second energy level, we encounter our first P sublevel. So we have 2P, 3P, 4P, and so on, and so on, and so on. In the third energy level, that is the first one that's large enough to include a D. So we begin to add that, and then the fourth energy level, that's the first time we would include an F. And actually, here's where we would first see a G. However, our ground state elements will not have any electrons in the G sublevel. So vertically, this shows us the sublevels that are contained in each energy level. Again, a reminder, a difference between the 1s and the 2s. S, by definition, only includes the s orbital, can only hold a total of 2 electrons. So even though the 2s is further from the nucleus and therefore larger in energy, it's still, any of these can only hold 2 total electrons. Any of these, a total of 6. Any of these, a total of 10. Any of these, a total of 14. If we create diagonal lines, and if we follow these from tail to tip, they guide how we place electrons in the atom from lowest to then higher energy and higher and higher and higher and higher. So if we follow this chart, it actually will guarantee the off-Baugh principle is being followed. For example, let's create the electron configuration for helium. Helium contains a total of 2 electrons. We always start at the 1s. The 1s can hold a total of 2 electrons. That's all we need. That is the electron configuration for helium. The electron configuration identifies sublevels and the exponents that are in the sublevels by superscripts. Remember, the energy level, that is the principal quantum number, and the sublevel, that is that L quantum number. If we would do for lithium, which has 3 electrons, we'd always start at the 1s. The 1s can hold 2. Do we need a 2? Absolutely. We fill the maximum capacity before we move onward. So the third electron will go to the next arrow, and that is the 2s. The 2s can hold 2 electrons, but we don't need it to. We only need it to hold 1 for a total of 3 electrons for lithium. Let's go now to fluorine. Fluorine has 9 total electrons. Where do we start? The 1s. The 1s can hold 2. Do we need it to? Absolutely. We have 7 more. The 2s is next. We'll fill it to capacity. There's 4, we need 5 more. So the next arrow is 2p. 2p can hold up to 6. However, here we only need it to hold 5 for a total of 9 for fluorine. Let's do nickel. Nickel in the neutral state has 28 total electrons. Let's start at the 1s. That can hold 2. Then the 2s. That holds 2. Next, the 2p. Do we need it to hold the capacity of 6? Yes, that is a total of 10. And again, nickel has 28. So then we go, after 2p, to 3s. 3s can hold 2. After the 3s2, then we would proceed to the 3p. The 3p can hold a total of 6. So if we do an accounting, we have 2, 4, 10, 12, 18. So we have another 10. After 3p, 4s. There's another 2. So then we would go to 3d. Now 3d can hold 10, but we'll only need it to hold 8. And as we tally up, that gives us a total of 18 or 28 electrons, which is what we need for nickel. Let's do aluminum. Aluminum has 13. 1s2, then we would go to 2s, then 2p. That's a total of 10. 3 more. 3s. Now 3p can hold 6, but we only need it to hold 1. Those are examples of electron configuration. Orbital diagrams show arrows for electrons, either an arrow pointing up or an arrow pointing down. It's been experimentally proven that electrons have an axis that they rotate around. Electrons can rotate, though, in a clockwise or a counterclockwise fashion. We use an arrow pointing up, even though you're not responsible for knowing this connection, to symbolize clockwise, and spin down or pointing down to symbolize counterclockwise. It's been measured and proven that electrons travel in pairs. Well, we understand that whenever they pair up, they pair with opposite spins. And that gives an extra level of stability that overcomes the normal repulsion that electrons would have for each other when they come near. So if we ever pair up electrons, they will have opposite spins, just like that. It would be incorrect to show them both spinning clockwise or both spinning counterclockwise. So orbital diagrams are a little bit more beyond electron configurations. We show electrons by using arrows, and we show orbitals with dashes. Remember, the s sublevel has one s orbital. So for example, the 3s, we would just have one dash because the 3s sublevel only has one s orbital. But the 3p, the p sublevel, has 3 orbitals. So we would show 3 dashes. So the 3p would be 3 dashes. The 4p would be 3 dashes. The 5p. And to just not make it so crowded, usually whenever we're writing a p sublevel, we write the 3 orbitals fairly close and just write once that it would be the 2p or the 3p or whichever p we're representing. Now, if we're writing D, remember D has 5 orbitals in its sublevel. So if we were putting electrons in the 4D, we'd write 5 dashes or 5D or 6D, and then we'd collectively show that these all belonged. All right. Well, the Pauli exclusion principle is what actually governs electron pairs having opposite spins. There's something called Hund's rule. And Hund's rule says this: whenever we are putting electrons in orbitals of equal energy, so all the p would have orbitals of equal energy, the 2p, the 3p, the 4p. The orbitals within a d sublevel would have equal energy, the 3d, the 4d, and so on. For example, these 5 orbitals in the 6d all have equal energy, hence why I kind of put them, close to each other in all the same line. Well, the same thing here. These would have all the same energy. Whenever we are putting electrons in orbitals of equal energy, they will be put by themselves first and then doubled up with opposite spin. By themselves first and then doubled up with opposite spin to follow the Pauli exclusion principle, but also Hund's rule. All right, so let's take a look at some of these. So I thought I would do orbital diagrams right along with the electron configurations I've done. All right, so for helium, this is the electron configuration, but the orbital diagram, the 1s sublevel has one orbital, 1 dash, and I need to identify it's the 1s. I do not put a superscript like I did for the electron configuration. In electron configuration, a superscript shows electrons, but in an orbital diagram, arrows. Helium has 2 electrons. They are in the 1s, but the Pauli exclusion principle, they will have opposite spin. It doesn't matter if you show the arrow pointing up and then the down, or the down first and then the up, just as long as they have opposite spin. And that's it for helium. The orbital diagram for lithium. Well, 1s has 1 orbital. 2s has 1 orbital because they're s's. That's what they have. This has 2 electrons. They will be traveling with opposite spin. There's only 1 electron here, and it is up to you. You can have it pointing up or pointing down. Both are correct. I just like to be consistent, and I always point up first. So this would be for lithium. All right. How about for fluorine? Well, the orbital diagram, 1 dash for the orbital within the 1s sublevel, 1 dash for the 2s, but for P, there are 3. And I'm going to collectively write 2P, and we can see I've separated and kind of identified, those belong to 2P. Here, filled with opposite spin, filled opposite spin. But here, I will place 1 electron here. This is Hund's rule. The second equal energy orbital will go here. The third will go here. Now, these are equal energy. You could have placed here, and then here, and then here. Or here, and here, and here. It does not matter. But usually I just like to go left to right. We have 5. So 1, 2, 3. Now it's up to you. You can put the 4th anywhere, but it must have opposite spin. So I just like to go left to right. 1, 2, 3, 4, and then 5. Now, questions that we can answer with orbital diagrams. How many paired electrons do we have? How many